Okay, so we're starting with 1a obviously, and without using a substitution, so some other means, can you integrate 2x over x squared subtract 1 with respect to x? Okay, so please pause the video and try it. Okay, let's have a look at the solution. Okay, so for the first question, we are asked to integrate with respect to x 2x over x squared minus 1. It's a fraction. So when you're asked to integrate something of this form, it's a good idea to ask yourself a series of questions about how to go about this. Now the first question to ask yourself is the numerator the derivative of the denominator? Because there is a very nice result that we saw when we did differentiation. Now just to generalize this result, and we'll see how it applies here. If I have some function which is a natural log, so let's say we have the natural log of f of x, like that. Okay, now if I want to differentiate that, so I'm going to d by dx both sides. So if I want to differentiate that, okay, you may remember that the result is rather nice. You get the derivative of the function over the function itself. Okay, now that was a really nice result that we saw in differentiation, and it can be applied very, very quickly. So let's suppose we want to use this in reverse. Okay, so let's suppose I want to integrate this. Well, we can see clearly, I mean, the implication is obvious. Okay, so that means that if I want to integrate something of the form f dash x over f of x, the derivative over the function, with respect to x, I'm going to get the natural log of the function back. Okay, and you would obviously have a constant of integration as well. Now notice I've just taken a precaution of putting a modulus around the function because you cannot take the log of a negative number, but that's just a precaution. Okay, so let's test our question. So we've got 2x over x squared minus 1. So just very quickly, the denominator is x squared minus 1. Okay, and if you just quickly differentiate that, you'll notice you will get 2x. Okay, now this checks out. This means that my numerator is indeed the derivative of my denominator. So I can just write down the answer. So the actual answer, I mean, you don't have to do all this work, of course. This is just me talking you through the thought process. So we can just write down the answer now as equals, pen's running out already, so that's going to equal, let's try that again, that's better. Okay, so it's just going to be the natural log, and just put our modulus sign in as a precaution, remember. So remember the function is on the bottom, so it's the natural log of x squared subtract 1 plus the constant of integration. Okay, and we're finished. Okay, so for 1b, again, without using a substitution, can you integrate 2x subtract 1 in the numerator over x subtract 2 multiplying x plus 1 in the denominator, or with respect to x? Okay, so please pause the video and try it. Okay, let's have a look at the solution. Okay, so for 1b, we are asked to integrate another rational function. This time we have 2x minus 1 over the product of two factors, x minus 2 and x plus 1. So a good natural thing to do would be just to expand the denominator and see what we have, because hopefully we can apply the same principle as we applied in part A. Alright, so I'll just expand the denominator. So that's going to give me the integral of 2x subtract 1 over, so just write this out as a quadratic expression. That's going to be x squared. So that's going to be plus x subtract 2x. That's going to be subtract x subtract 2 dx over here. Okay, so that's rather good. Now again, let's ask ourselves that series of questions. We didn't actually get on to the next questions. We'll discuss that later. But the first question is the numerator the derivative of the denominator? So let's just quickly differentiate the denominator as we did previously. So this is just a little bit of rough work as an aside. Okay, so if I just do that, we are going to have x squared subtract x subtract 2. Now if I just differentiate that quickly, that's going to give me 2x subtract 1. Okay, brilliant. Okay, so we now know that the numerator is indeed the derivative of the denominator, and we can apply our result yet again. Okay, so let's see where this is going to head in the future questions. So this is going to equal the natural log. Let me just write down the answer now. No more work to do. Of the modulus of x squared subtract x subtract 2, and not forgetting the constant of integration. Okay, there we go. So in 2a, using what we have learned in question 1, can you integrate x over x squared subtract 1 with respect to x? Okay, please pause the video and try it. Okay, let's have a look at the solution. Alright, so for question 2a, this is very, very similar to question 1a. We are asked to integrate x over x squared subtract 1 with respect to x. So we can probably tell already this approach that we've adopted in the first two questions will fail. Okay, so let's just do a check anyway. Is the top the derivative of the bottom? Well, we already know that it's not going to work, but I'll just put it in there anyway. So x squared subtract 1 differentiates to 2x, as you know, which we used in 1a. So unfortunately, it's not the same as the numerator. But can we salvage something from this? Because it would be a shame to have a numerator so similar to this and not be able to use our result. So what I would dearly love is to apply this result and get this over quickly. So is there some way I can manipulate the question so that I can use this result again? And the answer is yes, we can. So I'm just going to rewrite the question as follows. So this is going to equal the integral of x over x squared subtract 1 dx. Now, wouldn't it be great if I could have a 2x in the numerator? Wouldn't that just work out brilliantly? Okay, because then we would have the same answer as we had in 1a. Now, yes, I can use that. Now, unfortunately, because it's x and not 2x, I have to obviously do something to this to cancel out the fact that I've doubled it. And I can do that because I can multiply my integral by 1/2. So, I hope you can see this. If I put 1/2 as a multiplicative constant at the front of my integral, okay, the half and the 2 will cancel. So I am in fact integrating the same thing. They are identical statements. And notice now I can use my result. So the answer is now really straightforward. Okay, so it's just going to be 1/2 this time of the natural log of x squared subtract 1 plus the constant of integration. Okay, so I've managed to salvage this question just by doing a little bit of manipulation in the integrand. Okay. And again, in a similar fashion for 2b, use what we have learned in question 1. Can you integrate 1 subtract 2x over the product of x subtract 2 and x plus 1 in the denominator? Okay, all with respect to x. So please pause the video and try this. Okay, let's have a look at the solution. Alright, so in question 2b, we have again a very similar situation to 1b, so you can probably tell the aim of this. I've taken the liberty of just doing the first step, so I've expanded the denominator, so we have x squared subtract x subtract 2. Now remember from question 1b, I'll just perform that differentiation again. We need to check whether the numerator is the derivative of the denominator, so I'll just do that. So remember that x squared subtract x subtract 2 differentiates to 2x subtract 1. Alright, just a bit of side work there. Okay, so you shouldn't really use this notation, but this is just the thought process. So the 2x subtract 1 is what I should have in my numerator if I were to use the log function as my integral. Okay, well, I don't have that, but again, is there some way I can salvage this question? So let's have a look. We've got 2x subtract 1, that's our desired numerator, that's what we would like to have. I have 1 subtract 2x. Okay, so let's just pause and think. How can I manipulate this somehow so that I can use this? Well, notice that 2x subtract 1 and 1 subtract 2x are the negative versions of each other. Okay, so if I just multiply all this by -1, I will get this. So that's the step. So what I will do is I will write out the integral again with this added -1 multiplier. So it's going to equal, so this is carrying on from step 2 here, it's going to equal the integral of 2x subtract 1, which is my desired numerator, over x squared subtract x subtract 2 dx. Okay, and remember, I can use this because if I multiply the entire numerator by -1, as I'm doing here, okay, that will give me -2x plus 1, which is the same as step 2 and step 1, of course. So I can now apply my result. So the final answer will be, here we go, negative natural log of the modulus of x squared subtract x subtract 2 plus c. And there we go. And if you like, it's a nice exercise, of course, to try and differentiate these answers and show that you actually get back to the original integrand. Okay, and we'll stop there. So now in question 3, we are asked to express in partial fractions x plus 5 over the product of x subtract 1 and x plus 2. Okay, please pause the video and try it. Okay, let's have a look at how to do this. Okay, so in excuse me, the next question, this is question 3, we have to express this rational expression as partial fractions. Now, if you notice, in this case we have a linear expression in the numerator and 2 linear expressions multiplied together in the denominator. Now, just mention how to set up the partial fractions, because we need to know a little bit about the fraction before we start this. Now, if you expanded the denominator, you would realise quickly that this is a quadratic. In fact, you would know this just by looking at it, because you've got an x multiplied by an x. So it has an order of 2. So if I just make a note of that, it's got an order of 2. Just talking about something called order, which is the highest power of x in the expression. The numerator has an order of 1 because it's just a linear expression. So if I write, just make a note of that as well. Now, because the order of the numerator is 1 less than the order of the the order of the denominator, that means that we have a proper fraction. Okay, so I'll just make a note. This is just for your reference. So because the 1 is less than 2, that means we have a proper fraction. Now, the implication of this, it's very faint, isn't it? The implication of this is that we don't need to use anything like long division of algebra or anything like that. We can just express these as two linear fractions. Okay, so this is the partial fraction decomposition. All right, so we learned how to do this in the very early on in the course. I think it was very early on in year 2 when we were looking at algebraic fractions. So we write an identity sign because this is an identical expression that I'm going to write down on the right hand side. So because we have two different linear factors in the denominator, we express them as separate partial fractions like so. So what we have is we have the x minus 1 factor appears here. Okay, now because this is a proper fraction, the order of the numerator must again be less than the denominator. Now, to get an order less than 1, that's an order of 0. So the highest power of x has to be x to the power 0, which effectively means a constant. So that's why we have a constant a in the numerator. And the same thing with b over here over x plus 2. Okay, so let's actually go ahead and write this expression as two separate partial fractions. Now the way to do this is just to simply try and reconstruct the left hand side using what we've got on the right hand side. That will determine what a and b are. Okay, so what I'm going to do is I'm going to write out the two fractions again. So it's going to be x subtract 1 and then a, and then I'm going to add b and x plus 2. Okay, now we want to combine these two fractions, so what I need to do is find a common denominator. So if I multiply again these fractions, sorry, I beg your pardon, these expressions together, I will get the same denominator. So that's the key, isn't it? If I express both fractions over x subtract 1 and x plus 2, I've then got two fractions that I can combine. So I'll do that in a different colour. So we've got x subtract 1, so I'm going to be multiplying that by x plus 2 in the denominator, and over here I have x plus 2, so I need to multiply that by x subtract 1. Now I'm allowed to do that, of course, provided that I don't change the fraction in any way, which means I have to multiply the numerators by the same factor. So a must be multiplied by x plus 2, and b must also be multiplied by x subtract 1, like that. Okay, so let's go ahead and combine these two fractions. So this is identical, of course, to what I've said previously. Okay, so we are going to have ax plus 2a plus bx subtract b. I'm just multiplying out the numerator as well, I hope that's okay, all over x subtract 1 multiplied by x plus 2. Now then, we can now combine, we can compare numerators, because if this fraction here is identical to this fraction here, then the amount of x I have in the numerator here must be the same as the amount of x I have here. And similarly with the constants, my constants 2a and negative b must combine to give 5. Okay, so we need to work out what a and b are using equating coefficients. So I'm just going to make a note of what we've actually got here, because this is really important. Alright, so let's equate coefficients. Now I'll just do this over here so we've got a bit more room. So equate coefficients. Alright, so let's have a look at the x's first of all. So the x's, Now that's going to give me a plus b lots of x for what we've got here, which would be the right hand side, and that must equal 1. Okay, so I've got a plus b, which comes from this because I've got ax plus bx. That must equal 1 because I have just one x up here. Okay, so that's the first equation set up. Now let's have a look at the constants. So for the constants, which I'll just label as C, so constants, like that. I think I've already mentioned this, but I'll just say it again. So we've got 2 lots of A, subtract B as my constant terms, and that must equal 5. So I'll just write that down. So 2A subtract B equal to 5. Now notice here we have simultaneous equations. Okay, so let's number them 1 and 2. So equation 1 and equation 2. Alright, now what I can do now is I can combine the two equations. If I multiply 1 by 2, I should be able to subtract them. Or what I could do, if I just add them together, the b's will cancel. Okay, so let's do that. So if I do 1 plus 2, that's going to give me a really nice result very quickly. So it's going to give me 3a. Obviously, I'm assuming you know how to do this from earlier, well, last year, in fact. So that's 3a plus b and negative b, they cancel. So that's going to give me 6. Like that. And then that means that a equals 2. So I've got my a. Alright, and then we do the same thing for the b's. So I can use equation 1 again. So in 1, okay, a plus b equals 1. So that means that 2 plus b is equal to 1. So therefore b must equal negative 1. Like so. Right, so now we have our partial fraction set up. So before we finish, we just should write these out properly as is required. So I'll just rub out a bit of my line there so I can write this down. So my final partial fractions are going to be this. So we've got a over x minus 1, so that's going to be 2 over x subtract 1, and then b is negative, it's negative 1, so that would be minus 1 over x plus 2. Okay, I hope you can see that. So that's 2 over x subtract 1 minus 1 over x plus 2. Okay, and we're done. And lastly, we're asked to use polynomial long division or some other method to find the constants a and b in this case. So in other words, expressing 3x subtract 5 over x subtract 1 as partial fractions. Okay, so please pause the video and have a go at this. Okay, so let's have a look at the answer. So in question 4, which is the last question, we are asked to use polynomial long division or otherwise to express this rational expression in partial fractions. Now, just a word of advice, if this was an exam question and it said or otherwise, just please ignore the or otherwise bit, okay, and use the guidance that they give you. So in this case, I could use equating coefficients, but I am actually going to use polynomial long division, simply because I used equating coefficients in the previous question. Alright, so let's just have a little chat about the order again of what we have here. So let's just see what we're expecting to get. So the question actually states that we will get a constant plus a rational term, which is b over x subtract 1. Now, I'm not going to write that down. I'm just going to talk about why that is. So if you look at the denominator here, like we mentioned earlier about the order, the denominator here has an order of 1. Okay, but that means that the highest power of x is x to the power 1. Similarly, the numerator also has an order of 1. So we don't have a situation like in question 3 where the numerator has an order less than the denominator. So this is not a proper fraction. This is going to be an improper fraction, okay? Which is why you get the constant term first. So you can think of it like converting an improper fraction to a mixed number. It's the same principle. Okay, so let's do the division. So this is good practice, good revision in fact. So let's set up the bus stop, as we like to call it. So we're going to have x minus 1 is the divisor, so that's going to go on the outside of your bus stop. Okay, and then we'll draw the big bus stop here, like that. Okay, it probably doesn't need to be that big, but there you go. Okay, and the expression I'm dividing by, or not dividing into, I apologise, is 3x subtract 5. Okay, now let's just go through the process. So to do polynomial long division, we look at the first term in each of these expressions. So I'm going to look at the x part here and the 3x part there, and we divide the 3x by the x. Okay, so we can do that in our heads. So if I divide 3x by x, the x's will cancel and will leave me with 3. So 3 is a constant, so I write the 3 in what I like to call the constant column, okay, which sits directly above the -5 where the other constant lies. So that means that I have a quotient of 3. Okay, the quotient is finished because it's the final, it's in line with the final term in our expression here. So what I do now I've got my quotient, I take the quotient part that I've just got and I multiply it by my divisor here. And I write the result underneath the 3x subtract 5. So let's do that. So I do 3 multiplying x subtract 1. Okay, so that's going to give me 3x. And then 3 multiplying -1 gives me -3. Okay, and now I subtract the bottom expression from the top. So I always like to just put a little subtraction symbol here just to remind me that I am subtracting every time. Okay, so let's do that. So I do my subtraction, I'll just rule that off. So 3x subtract 3x cancels, as it always should. And then I have to be very careful here. I have -5 subtract -3. So in effect I've got -5 add 3, which will give me -2. Okay, so that's -2. Okay, and we're finished. So there's nothing else to do. So let's just have a look what we've got here. So remember, this is my divisor here. Okay, that's my divisor. This is my quotient up at the top, and you'll probably guess the -2 is the remainder. Okay, so I can write my answer down now. I like that process because it just feels very, very quick compared to equating coefficients. But if you want to use equated coefficients, you're more than welcome to do that, and we can compare answers. So 3x subtract 5 over x subtract 1 is identical to, now I've got my quotient first, so that's going to be 3. That's my a, because that's what I get. That's how many whole numbers I get, if you like. And then I have a remainder of -2, so subtract 2 over my divisor, which was 3. Sorry, I beg your pardon, x subtract 1. Okay, so with a bit of rearranging, you can check that these are in fact identical. Okay, and we'll stop there.